Right now, 6 miles above the ground, you are sitting inside an aluminum tube where the air on the other side of the window is minus 60 degrees Celsius. That is not an exaggeration. At cruising altitude, around 35,000 feet, the outside temperature is colder than almost anywhere on the surface of the planet. Colder than the deep Siberian winter. Colder than most of Antarctica. Cold enough that exposed skin would freeze in seconds, and cold enough that jet fuel itself begins to thicken towards slush. And yet, the air around you is a mild 22 degrees. You might even be a little too warm. You might have just asked for a cup of coffee and slipped off your jacket. The window beside you is a thin sheet away from an environment that would kill an unprotected human faster than almost anywhere on Earth. And you're worried about whether the person in front is going to recline their seat. Here is the strange part, the part almost nobody thinks about. There is not a single heater on this airplane, no furnace, no electric heating coil, no gas burner. Nothing on board was designed and built for the specific job of making heat. If you walked the entire length of that jet and opened every panel, every compartment, every service hatch, you would not find one device you could point to and say, that is the heater. It simply does not exist. So where is the warmth coming from? How does a machine with no heater keep 400 people comfortable while sitting in air cold enough to kill them? Why did the engineers deliberately choose not to install one? Not because they forgot, but on purpose. And here is the question that turns the whole thing upside down. Why is the real challenge in flight not heating the cabin at all, but cooling it? Let's open up this machine and find out. Before we climb inside the system, if you like the hidden engineering behind the machines that move our world, take a second and subscribe. It genuinely helps this channel keep going. So let's start where most people start, the obvious answer. You'd assume that somewhere in the belly of the plane, there must be a heater. Your house has one. Your car has one. Every enclosed space you've ever been warm inside had a dedicated machine whose entire purpose was to produce heat. So surely something flying through air, this cold, needs a big, powerful furnace working overtime. Maybe a bank of them humming away under the floor. It's a reasonable guess, and it's completely wrong. Think about what a heater actually needs. A heater needs energy, a lot of it, to create heat from nothing. In your home, that energy comes from burning gas or from electricity pushed through a glowing coil. Now scale that up. You are not trying to warm a bedroom. You are trying to hold an entire aircraft cabin, a space the length of a tennis court, wrapped in thin metal, at a pleasant temperature while the outside is 80 degrees colder. And you have to do it not for an hour, but for a 14-hour flight across the Pacific, without stopping, without refueling a separate heating system, without ever failing. To do that with a dedicated electric heater, you'd need an enormous amount of onboard power and a heavy, hungry heating system to match. And here's the thing about aircraft that people on the ground never quite feel in their bones. Every single kilogram costs money for the entire life of the airplane. Weight means fuel. Fuel means cost. And cost means the whole thing only makes sense if you are ruthless about what you carry. Engineers fight over grams. They drill holes in metal brackets to shave weight. They redesign a coffee maker mount to save a few hundred grams across a fleet. The idea of bolting in a giant furnace. Heavy, power-hungry. One more thing that can break at 35,000 feet is, to an aircraft designer, almost offensive. So the designers asked a different question. Not how do we build a heater strong enough, they asked. We already have two of the most powerful heat-generating machines ever built bolted to the wings. Why on earth would we build a third one? They were talking about the engines. And that single change in thinking is the whole secret. Here is how the cabin actually stays warm. A jet engine works by sucking in air at the front, squeezing it hard, mixing it with fuel, and burning it. Before that air ever reaches the fire, it passes through the compressor. A series of spinning blades, stage after stage, that pack the incoming air tighter and tighter. And when you compress air, something happens that is easy to forget from a school physics lesson. Squeezing a gas heats it up. Not a little, a lot. By the time air has worked its way through the compressor stages of a large jet engine, it is under enormous pressure, and it is scorching hot. Engineers tap into that stream deliberately. They open small valves at specific points in the compressor and bleed off a portion of this hot, compressed air. That is the actual name for it, bleed air. There's nothing gentle about the word. And there's nothing gentle about the air. Bleed air leaving the engine is somewhere around 200 to 250 degrees Celsius. In the deeper stages of the compressor, before it's tapped, the air can approach 1,000 degrees Fahrenheit. Hotter than a self-cleaning oven running at full blast. Hot enough to glow, hot enough to melt many plastics on contact. This is not warm air. This is a fire hose of heat. And that is the secret. The plane isn't heated by a heater. It's heated by a tiny fraction of the same superheated air the engines are already producing every single second they run. The heat is free. It is a byproduct of keeping the airplane in the sky. The engineers looked at that river of scorching air pouring through the engine and refused to waste even a sip of it. So there is no furnace on board because there does not need to be one. The furnace is spinning on the wing at 10,000 revolutions per minute, and it happens to also be the thing keeping you aloft. 2 jobs, 1 machine, and bleed air doesn't only warm the cabin. The exact same tapped air is used to pressurize the cabin so you can breathe at altitude, to run the anti-ice systems, to start the other engine, and more. One stream of hot compressed air, quietly doing half a dozen critical jobs at once. It might be the single most reused resource on the entire aircraft. And now we arrive at the part that breaks people's brains. You would think that at minus 60 degrees outside, the entire challenge is fighting the cold. That the system is desperately clawing to add warmth, straining against that hostile freezing world pressing on the windows. But it is the opposite. The system spends most of its effort throwing heat away. Remember, that bleed air is 250 degrees. It is far, far too hot to breathe. 250 degrees would scald your lungs instantly. It would blister skin on contact. You cannot pipe that directly into a cabin full of people. So before a single molecule of it reaches you, the aircraft has to cool it down, dramatically, violently, from oven hot to room temperature in a matter of seconds. This is where a piece of equipment called the air conditioning pack comes in. And here is a detail that ought to feel absurd. On an airliner freezing in minus 60 air, the single most important environmental device is literally an air conditioner. There are usually 2 of them tucked into the belly of the aircraft near the wings, and they run constantly. Inside each pack is something called an air cycle machine. Think of it as a glorified radiator married to a turbine. First, that blistering hot bleed air is run through heat exchangers. And what cools those heat exchangers is the frigid outside air scooped in through intakes. So the minus 60 air you'd assume is the enemy is actually recruited as the coolant. The plane uses the killing cold outside to tame the killing heat inside. Then, the pre-cooled air is forced through a small turbine and allowed to expand rapidly. And here's the beautiful part of the physics. When compressed air is allowed to expand, it cools. The exact reverse of what happened back in the engine compressor. Squeezing heats, releasing chills. The pack can take air that entered at 200 degrees and in one pass, drop it to near freezing or even below. Then, at the very end of the whole process, the system does something that sounds almost comical after all that effort. It takes that now cold air and blends a little bit of the untouched, still hot bleed air back into it. Just a pinch, to bring it up to that comfortable 22 degrees before it flows out of the vents above your seat. Read that back slowly. The airplane heats the air by cooling it first, then adding a measured trickle of heat back in. Because the raw ingredient it starts with, engine bleed air, is so violently hot that the real engineering problem, even at minus 60, is getting rid of excess heat, not manufacturing it. The thermostat over your seat isn't turning a heater up and down. It's adjusting how much scorching bleed air gets mixed back into an already cooled stream. The enemy the system fights hardest isn't the cold, it's the heat it already has too much of. Now, if the plane has heat to spare, why does the cabin still sometimes feel cold? Why are your feet freezing on a long night flight while your face feels fine? Because the cold does get in, just not the way you'd expect, and not where you'd expect. The fuselage is a thin metal skin. On the other side of that skin is -60. Metal is a superb conductor of heat, so the cold soaks inward through the structure, especially low down near the floor and along the walls. That's why the floor and the area around the windows are the coldest parts of the cabin. The warm air is pouring from vents above you, but the chill is seeping in from the shell around you. Your feet sit closest to the coldest surface, which is exactly why experienced long-haul travelers bring socks and keep something over their legs. The windows are their own small engineering story. They aren't a single pane, they're multiple layers with a gap, and there's a tiny hole, the bleed hole. In the inner pane you can sometimes spot. That little hole balances pressure between the layers and helps control fogging and frost, so the window doesn't ice over from the inside as warm cabin moisture meets that freezing outer pane. Without careful design, you'd be scraping frost off the inside of the window at cruise. So the picture is subtler than heater versus cold. It's a constant, moving balance. Warm conditioned air flooding in from above, cold conductive chill creeping in from the shell below, and a system quietly holding the whole cabin in equilibrium. When it feels a touch cold, it usually isn't that the plane ran out of heat. It's that the warm air simply hasn't reached the coldest low corners where you happen to be sitting. So if the cold outside isn't the true threat, and even the drafty floor is just a nuisance, what is the real danger? The real enemy is losing the source. Everything, the warmth, the breathable pressurized air, all of it, depends on the engines running and those bleed valves staying open. The cabin does not hold a reserve of warmth in a tank somewhere. It is being continuously fed, moment by moment, breath by air freshly bled from the engines. Cut off that feed, and the comfortable little world you're sitting in starts to unravel fast. Consider the airplane sitting at the gate with its main engines shut down. Suddenly, there is no bleed air at all. No source of heat, no source of pressurization, nothing conditioning the cabin. On a freezing winter morning, that cabin would grow cold quickly, and on a blazing summer afternoon, it would turn into an oven just as fast. This is why every airliner carries a small extra engine buried in the tail called the Auxiliary Power Unit, the APU. It's essentially a miniature jet engine, whose entire job on the ground is to produce bleed air and electricity, while the big engines are off. When you board and hear that steady whine before the main engines spin up, that's the APU, quietly keeping the cabin alive. And when the APU isn't running, ground crews sometimes plug in a big yellow hose from a cart to pump conditioned air aboard, a temporary substitute for the missing engine breath. Then there's a second, rarer danger, and it comes from the very intimacy of this system. That bleed air is tapped from deep inside a running jet engine, a place full of hot oil and spinning seals. If one of those seals begins to fail, traces of oil can find their way into the bleed air, and passengers or crew might notice an odd smell, sometimes described as dirty socks or hot oil. Crews call this a fume event. It is uncommon. Modern systems are designed to detect and isolate it, and pilots train for it. But it exists precisely because the air you breathe has been drawn straight from the beating heart of an engine. The comfort has a source, and that source is a machine running at the edge of what metal can endure. And in the extreme case, a sudden loss of cabin pressure, the same truth bites hardest. The warm, dense, breathable air you've been enjoying is only there because the system is pumping it in faster than it leaks out. Break that balance, and within moments the cabin climbs toward the freezing, airless reality outside. That's what the oxygen masks are for. That's why the crew would descend rapidly to thicker air. The whole comfortable illusion depends, second by second, on the source holding. So understand the twist fully. The threat was never really the -60 outside your window. -60 is just the backdrop. The true threat is anything that interrupts the flow of hot, life-giving air from the machines doing the work. Now, none of this runs itself in the effortless way passengers imagine. Someone is always watching it. Up in the cockpit, the pilots manage what's called the pneumatic and air conditioning system. That whole network of bleed valves, packs, ducts, and crossover lines we've been describing. On the overhead panel, there are switches for each bleed source, each pack, and the valves that let one engine feed the entire airplane if the other has to be shut down. During the climb, during the descent, and any time a gauge reads even slightly abnormal, the crew is cross-checking pressures and temperatures against what they should be. And here is where you see plainly why there are always two pilots and not one. Air system problems are quiet. They don't announce themselves with a bang or a flash. A slowly failing pack, a bleed valve drifting shut, a hot air duct leaking behind a panel. These show up as a needle creeping a few degrees the wrong way, a pressure reading that's just slightly off, a temperature that isn't quite settling where it should. Those are exactly the kind of small, silent signals a single tired human misses at the end of a 10-hour night flight. A person alone doesn't notice himself getting slower, doesn't notice the one gauge among dozens that has quietly wandered. Two people check each other. One flies the airplane. The other can put their head down, run the checklist, isolate a bad bleed valve, and bring the system back under control. Redundancy here isn't a luxury. It's the difference between a line in the maintenance logbook and an emergency descent with masks deployed. There's something almost human about the entire arrangement when you sit with it. The airplane does not care that it's -60 outside. The engine does not care whether you are comfortable, whether it's Christmas, whether you're asleep. The warmth you feel is not the machine being kind. It is a byproduct, the raw, indifferent violence of a jet engine, captured, cooled, measured, and routed by people who designed it decades ago, and by two people up front watching it right now. That is what turns a fire hose of 200-degree air into a cabin quiet enough to sleep in. Step back, and the cleverness of all this only grows. Early aircraft had none of it. Open cockpit pilots in the 1920s and 30s simply froze. They climbed into unheated, unpressurized cockpits wrapped in leather and fur, some wearing crude electrically heated suits, and they still landed with frostbite on their faces and hands. There was no warm cabin to retreat to, because there was no cabin at all in the modern sense. Just a man, a windscreen, and the murderous cold of altitude. Flying high was quite literally a battle against freezing and against the thinning air that could knock a pilot unconscious. The warm, shirt-sleeve environment we now take for granted only arrived with pressurization in the 1940s. And once engineers had committed to sealing the cabin and pumping conditioned air into it to let people breathe at altitude, using the engine's own bleed air to do the job was the obvious, elegant solution. They were already going to pipe engine air in for pressure and oxygen. Heating the cabin with the same hot stream cost them almost nothing extra. The heater was never removed from the design. It was never there to begin with, because a better answer arrived first. And the scale of what that free byproduct achieves borders on the absurd. A large airliner's engines produce so much bleed air that the system can pressurize a cabin holding hundreds of people, hold it at a steady, comfortable temperature, and completely exchange the air in that cabin every few minutes. All from a sip of the flow the engines generate anyway. The very same hot air is piped out to the leading edges of the wings and the engine inlets to melt ice off them in flight, keeping the aircraft's shape clean and safe. One free stream doing 3 or 4 life-critical jobs simultaneously for the entire duration of every flight. Then there is the strangest example of all, the one that proves the entire point of this video in the most extreme way imaginable. The Concorde. Flying at twice the speed of sound, friction between the aircraft's skin and the air heated the outside of that jet to well over 100 degrees Celsius. The nose grew several inches longer in flight from thermal expansion alone. A supersonic airliner's environmental problem was never a cold cabin. It was shedding heat, desperately dumping the warmth that friction poured into the structure. Concorde used its own fuel, sloshing through the airframe, as a heat sink to soak up some of that heat, which is the whole lesson of this video, taken to its furthest edge. Up there, in the thin, freezing, screaming air miles above the world, the machines that carry us are almost never fighting to stay warm. They are fighting to stay cool. So the next time you settle into your seat, look out at that frozen white world sliding past the window, -60, airless, utterly hostile. And remember that the warmth wrapped around you was never made by a heater. It was borrowed from the fire on the wing, tamed, cooled, and measured out to you one quiet breath at a time. There's something quietly beautiful about a machine that keeps you warm without ever building a heater. The engineers looked at the coldest, most hostile place a human body regularly travels through. 6 miles up, -60, thin enough to kill in minutes, and instead of fighting it with brute force and a giant furnace, they reached into the engine and borrowed the heat that was already there. No furnace, no wasted energy, just the leftover breath of a running engine, cooled, balanced, and shaped into comfort. Most of us will never think about any of it. We'll doze, sip our drink, tug a blanket over our knees, and grumble that the cabin's a little too warm, never knowing that a little too warm is the system working exactly as designed, in air that would freeze us solid in the time it takes to read this sentence. Every flight you've ever taken, that invisible machinery held the line for you the whole way. If you made it this far, hit like. It tells me you want more of these hidden engineering deep dives. And tell me in the comments, did you ever imagine there was no heater on the plane at all? I read every reply.